Okay, this shall be the last topic for the course, and it's quite an important one. As I mentioned, we only try to introduce you to the idea about recursion, which is quite a tricky topic, but you will be revisiting this topic over and over throughout the rest of your degree, especially 2011, when you talk about tree and graphs. But I'll try to give you at least the basics, okay? So now, let me just do this slide first, just to tell you what you should really do in order to practice recursion. If you only try to listen to the lecture, which is nice, but it wouldn't be enough to really completely grasp the idea about recursion, all right? Yeah, all right. So I would suggest at least 2 places you can go. First of all, if you go to these 2 websites, it's something called Coding Bet. It's actually online exercise platform. I'll show you how it looks like. If you click on the link, there are 2 links for you. So you go there, just go under Java. They got lots of problems over there for you to practice. If you click on any one of them, for example, Factorial, which we will talk about today as the first example, you can simply do your Java code over here. You have some problem description here, do your Java code recursively, and then you say go. It's going to run the various tests for you to practice. I would say try to really complete every problem over here. So I got 2 links over there for you. One is the basic one. And the second one is the more advanced. If you go there, it's fewer problems are more advanced. Try to complete them before the finishing of this course. Hopefully you'll get much better. But if you start with any of the questions, get in touch with me. Yes?
You can also create an account and it'll save all of your solutions. So
oh, really? Okay, sure. Yeah. Yeah, as your colleague suggested, you can also create an account so you can save all your work. Okay, just go to the website, it's free, and make use of that, okay? So in the class, we'll only talk about a few examples in detail, just to give you the feel about the principle, but you really gotta do practice. And there's another suggestion I will personally make. I think the best way for you to learn about recursion may not be using Java, okay? There is something that's not really part of the curriculum. There's some certain programming language called functional programming language. Okay? But this is completely optional. If you really want to dig into the idea about recursion, I would suggest start with a language called Haskell. Okay? It's quite a fun language. If you really are interested in that, also drop by my office hour. I can show you more examples. This part is optional. But the first part, I suggest you do before the end of the course or even before the exam. So you got a very good idea about recursion. Okay. Can you just know how many of you haven't learned recursion so far? Have not. Have not. Okay, that's okay, but I will assume everybody has know nothing about recursion. Let's start from scratch. Okay, and then we'll go a little bit faster after the first few examples. But today is going to be easy, light. So now, recursion basically is just about solving the problem recursively. But what do I really mean recursively? I want you to, maybe after today, just go back to your math notes. You learn about something called mathematical induction, right? You assume something in the base case, and then you try to assume something, and it proves something bigger. Recursion goes just like that, okay? So now, that's something I'll try to link to you in some later lecture. Let's just learn about the principle, okay? Make sure you understand the principle in general first, and then every time when you saw any new problem there and try to solve recursively, just apply that principle, okay? Now, recursion is very useful for expressing a solution for solving problem that can be described recursively. But what do I really mean by recursively? We'll see, okay? Basically, a problem can be defined by somehow itself. That's what it means to be recursive, okay? So there are 2 kinds of cases when you want to solve a problem recursively. I'll just show you the slides quickly, and I'll show you visually what that really means. You got base cases, which means the problem is so small right away, you can just solve them directly. Okay, just small base cases. And if the problem somehow is a little bit bigger than small, that means you cannot solve the problem right away. In this case, you have to somehow split the problem into different instances. Okay? So if the problem cannot be solved immediately, that means you have to somehow solve them by solving some smaller problems. And for those of you who are used to the fairy godmother analogy, right? Some of you might be. I'll try to link, maybe try to connect to it, if that makes you feel comfortable. If not, then don't worry. It's just analogy. Okay, we'll get there. So now solve solution by smaller problem, and then maybe try to review a little bit about mathematical induction. You'll see the linkage, okay? Now, let me just summarize visually in principle how you solve problems recursively. Okay, so I'll go over with you one by one, and then we'll solve problems all together. Now, how do you solve a problem recursively? Here's the principle, okay, recursively. If you're simply just given a small problem, like a blue one over here, very small conceptually, so small you can just get a solution in green right away. No more work to be done. On the other hand, typically, if you are given a bigger problem, let's say the bigger problem over here, apparently is bigger than the base one. So here are the steps. You will see the steps being applied for every problem we are trying to solve, okay? First of all, you have to split it somehow. For example, this is the originally big problem here. We'll split them into 1, 2, and 3 strictly smaller subproblems. You can see this subproblem over here is strictly smaller than the original one. And this middle one here is also strictly smaller than the original one, etc. Just split them somehow, okay? And then this is where the fairy godmother strategy analogy can come in. Simply, you say, given the smaller problem over here, I simply assume I can solve them individually because they're strictly smaller. And then, finally, the most important step. Given the solution to the strictly smaller problems over here, I'm going to somehow combine them. But how do I combine them? The combination can be, again, up to what the problem you're trying to solve. Sometimes it can be just adding up together. It can be multiply them together. Or it could be to concatenate them together. So when I say combine, it's a very general term. Okay, so basically split somehow, assume every one of them can be solved, and then somehow combine them. So these are the steps. Okay, and finally you can get the solution to the bigger problem. Okay, that's a general strategy. Is it clear? Just general strategy. And try to keep this general strategy in mind for every recursive program we're going to consider today and for the rest of the course. You're going to see all these cases. Smaller one, base case, and also for the bigger problem there, we're going to split and then assume, and then we're going to combine. Okay, so these are the steps. One more thing to mention. So how do you know a method is actually recursive? This is how you tell. Let's say if you have a method n, can be a mutator, can be an accessor, doesn't matter. Let's say we simply got an input value I over here. And somewhere in the body of this particular method here, you see that it's calling itself. Okay? If it is calling itself with another value, let's say j over here, and that means the method is recursive. Okay? But we'll talk about how you can make the recursive method in just one moment by learning from the examples. One thing I want to mention, if you have currently I here as the input, you're trying to so-called make a recursive call to the same method with just another value j. It is really important to know this j over here is more like a subproblem that we are talking about. Right? When you are given the blue, you want to split it into a smaller blue problem. So in this case, we'll say j is strictly less than I, conceptually. Okay? Okay, let's now see our very first example. Okay? And then we'll see how we can trace the recursive problem. Okay? Now let's see the Hello World program for recursion. Factorial. Okay? That's the, we'll do factorial, we'll do Fibonacci number, we'll do a few more today. And then we'll try to gradually get more complicated recursion for you. Okay, factorial. This is the mathematical definition for factorial, which means if n is simply equal to 0, you return 1. Or if n is simply equal to 1, you just return 1. Okay? Otherwise, if you got something that's larger than or equal to 1, it's simply going to be 1 multiplied by 2 all the way to n. Okay? That's the definition. Okay? Any question about factorial? We okay, right? Comfortable with it? Okay. Now, this definition over here is not recursive. Okay? Think about what we are doing here. We say that we want to calculate factorial of size n factorial. However, in the solution over here, we don't mention any factorial anymore over here, right? So that's not recursive. So how would a recursive solution to the factorial look like? Okay, let's see. A recursive solution would look like this. Okay, let me switch the iPad and tell you why it is factorial. Okay, let's have a look at just the mathematical definition over here first. So I claim this definition here to be recursive. But why is that recursive? Let's see. So let's just try to be very careful over here to define the terms. N factorial is the original problem I'm trying to solve. So that's the original problem that I'm trying to solve over here. Okay, so there are two cases. If n is simply equal to 0, n equals to 0 simply means the problem is so small problem. That means I can solve it right away by just giving you 1. Okay, that's case number 1. But what if n is larger than or equal to 1? That means it's considered as a big problem. So every time when you want to calculate factorial of a number that's larger than or equal to 1, we consider them as big, meaning that you cannot solve them right away. You have to do some recursive call. So how do we tell it's a recursion over here? So big problem, that means cannot solve right away. Cannot solve right away. Okay, let's see. Can you see where the recursion is in this case? We're somehow applying the definition itself, right? If you try to see this, I'll try to highlight it for you. If you look at over here, we're talking about the calculation for factorial, right? And the solution simply apply factorial itself. And then if you look at the size of the problem over here, the original problem over here has the size n. And the subproblem we are trying to mention is n minus 1. Right? You can see that over here. Let me just say this. If you think about this n minus 1 basically is the solution to a strictly smaller problem. And we simply assume it is going to work. And then if we can actually get n minus 1 factorial magically, let's say, if we can get it, so we should do something a little bit more to combine the result. And the combination will be whatever n minus 1 factorial result is, we're going to combine that with n. That's how we get the n factorial. Okay? So this part over here, let me just use a different color to show you. So over here, you're basically just to combine and to get the solution for the original problem. Okay? Guys, are we okay? Just for the general principle over here. The original problem you're trying to solve is n factorial. The size of the problem is simply n. But n either be too small or too big. If it is small enough, like if n is simply equal to 0, we can solve it right away just by returning 1 without any work. On the other hand, if somehow the value for n is strictly larger than 0, larger than or equal to 1, that means the problem cannot be solved right away. So what we got to do is we're going to split the problem into smaller problem. In this case, the smaller problem that we're talking about is n minus 1. As you can see, n minus 1 over here is strictly less than n. So we're trying to solve that smaller problem there, get its solution, and then try to apply something else and get the solution to the original problem, right? You will see this kind of process over and over for solving problem recursively. So, any questions so far before we see the Java code? Okay? And something I would like to emphasize, recursion is something quite mathematical. So I would say, usually if you are required to solve a problem recursively, you may want to come up with a solution that looks like the one I just mentioned, which is not exactly Java, it's just math. Okay? Once you get the mathematical solution that's defined recursively, you can translate it into Java. That's my general advice. Okay? Try not to just go to coding right away. It's easier to think about mathematically and then try to translate it into Java. Okay. Now, let's say we got this particular recursive mathematical solution already. How do we translate it to Java? It will be quite trivial. Okay? Basically, we're going to turn the explanation mark, which means factorial, into a method called factorial. Okay? And then, since we got two cases over here, so we also got two cases. We do the case analysis using if then else. We say that if n is equal to 0, which corresponds to this case over here, we simply say result will just be assigned to 1. Otherwise, that means this case over here, we cannot solve that right away. Then we'll simply say it's going to be factorial. You can see factorial here is calling itself. However, every time you make a recursive call, you want to make sure you're solving a strictly smaller problem. That's why we put n, -1 over here, okay? And then after you get a result of factorial n-1, you're going to combine that somehow with another expression. In this case, just n times factorial n-1, and then eventually to return it. Okay, are we okay so far? Just about programming. So now this exercise over here, I would say the value itself is not really about how to define that in Java, because it's rather trivial. But I think what's really important here is simple enough so we can try to understand how do you execute recursive method at the runtime. That's more important. Okay? So now let me erase this part here, and then let's trace it all together in detail. So I think it's really important for you to get that particular idea. Let me just erase this part here. And before I do that, let me just go over one slide together with you to see how you can trace it at the runtime. I'm going to talk about briefly some notion called stack. You will learn about how to implement a stack in 2011, next semester, right? But I'm just going to mention what, the minimum that you have to know about stack. It's a very easy idea, okay? Let me just open a new page on iPad, and then I'll switch, and then I'll show you. So what's really a stack? Very easy. Stack is a very simple data structure, just a particular way of organizing data, okay? The principle for stack is last in, first out. Okay? Conceptually, you can think about a stack that looks like this, just like a stack, okay? So let's say there are certain operations you can do for the stack. You can add something to it. You can also remove something out of it, okay? And we also got special names for add and remove. We don't just say add and remove. So for add, we say push, okay? And for remove, we simply say pop, okay? Just push and pop, okay? Just get used to the terms. Again, you don't have to understand how to implement a stack. You'll learn about it in 2011. Only learn about how to conceptually manipulate a stack. So I'm going to say push and pop from now on, okay? Now I'll give you one example. Let's say I want to say push, let's say a string called Alan, and then I want to push another string, Mark, and then I want to push another string, Tom. Okay, Alan, Mark, and Tom, okay? Now, the principle about last in, first out goes as follows. According to this, we're going in this order over here. Apparently, you can see that Tom is going to be the last element that's going to be pushed onto the stack. However, when you try to remove something from the stack, Tom is going to be the first one. That's why it's called last in and then first out. Okay, let's see exactly how that works. For the very first push, we're simply going to push Alan to the stack. Okay, and then we say that at the moment, Alan is so-called the top of the stack. Okay, and then we try to execute the second line. We say push and second element, and Mark is going to be stacked up over there. So we put Mark on top of Alan over here. So now, when we say the top of the stack is going to be changed to Mark, so that's now the top. Okay, and then if you try to execute the third one over here, push Tom. It's going to be stacked up again. So that's going to be Tom over here, and now Tom will be changed to the top of the stack. Okay, that's about pushing, okay, conceptually. Now, how do we remove stuff from the stack? This is how that works. Basically, you remove the current top. So now if I say, let's see this. If I say pop the stack, if I say that, it's going to choose the current top and remove it. In this case, it's going to be Tom. So now after removing Tom, the current top is now Mark. So that means if I try to say pop again, it's going to be removing Mark, right? So now Mark will be the second one. And then if I try again, so now Alan is now the new top. And then if I try to pop again, it's going to give me Alan. So now look at the order I'm trying to do. I push Alan followed by Mark followed by Tom. But when I try to retrieve, try to remove, try to pop the stack, I get the reverse order, Tom followed by Mark followed by Alan. Okay, that's how a stack works. Okay, any questions? That's all you have to know as far as the stack is concerned. Okay, so why can a stack be useful? Okay, stack can be useful in the following way. Okay, let me just explain to you conceptually. Let's say if I got a method over here, let's say M1. okay, just in general. Let's say I got some line of code over here, and then at some points, I try to call a helper method, M2, over here. At the runtime, how do we trace this particular code, okay? And the stack is exactly how the Java runtime monitors or keep track of your method execution. You can think about, first of all, we try to execute M1, so we have a stack to begin with, just empty. As soon as you start the execution for M1, you push M1 onto the stack, all right? And then we go something over here. As soon as we have to somehow call a helper method, the helper method itself may be M1 as well, if that's a recursive call. In this case, we're going to say, before we can finish M1 and pop it off the stack, we have to first finish M2. And then we simply push M2 onto the stack. If M2 itself also try to make another recursive call or helper method call, we have to stack up something else onto the stack. And as soon as M2 is finished, we can pop it off from M2, from the stack, and then we can continue for the rest of the M1, and then eventually pop it off M1. Okay? It's really the push and pop that we try to do on the stack at the runtime that we try to keep track of the method execution. Okay? That's just conceptually. Okay? So this is exactly how we're going to use to trace how a recursive execution is going to work. Okay? Any question about the stack, push and pop? Any questions? Okay. And in 2011, you're going to learn about how to implement a stack, which is also quite easy, but that's not a topic for this course. Okay, so now let's go back to Factorial, and then let's see how we can trace Factorial. Okay, that's the method that we talk about over here. Okay, can I just give you just 10 more seconds, please? Have a look at the code. Just make sure you're familiar with the structure. Okay, this particular one, and then we'll start tracing it. Okay, just make sure you're familiar with it. And notice that we do have some variable over here, result, which can be either reassigned to 1 or some recursive call, and then we eventually we return the result. Okay, just make sure you understand that part. And then we'll start tracing. Okay, let's try to trace. Okay, let's do it very carefully. Okay, basically what I want to trace is a particular call to Factorial with the input 4. That's what I want to do, Factorial 4. Now, let's see how we can do it. Okay, before and this is a runtime stack that I'm trying to use to trace it. Okay, before I try to get into the runtime stack, which is quite easy for you to get lost when things get more complicated. Before I do that, let me just show you another view of tracing recursion. So there are basically two ways of tracing recursion. Either you can use a stack, or you can use a tree. Okay, I'm going to show the tree version as well. Let's use the tree version first. Okay, let me just erase this part here, okay, to make it clean. So let's see how we can do it. Let's say I want to do Factorial 4. I would say fac over here, just for short. I want to do Factorial 4. How is it going to work? 4 over here is not going to satisfy this base case yet. You agree, right? Okay. So that means we have to make some recursive call to say n times Factorial n minus 1. That means in order to get the result for Factorial 4, I must do the following calculation. I must say 4 multiplied by Factorial 3. Agree? Okay. In order to get this, is this a base case yet? Factorial 3? No. Okay. In order to do that, I have to calculate 3 multiplied by Factorial 2. Factorial 2 is not a base case yet. So in order to do that, I have to further calculate 2 times Factorial 1. Now, is Factorial 1 a base case? Well, according to the code, not yet, right? Because 1 is still not exactly 0, so not yet, okay? So now, in order to do that, I got to do exactly like this. I got to say 1 times Factorial 0, right? Now, Factorial 0 is a base case, right? So now, this is where the things will get returned. So I know that Factorial 0 is a small problem for me to solve right away, which is going to be just 1. 1 here, and now 1 times 1 will give me 1. So that means for Factorial 1, I will get a result 1. And then for 2 over here, 2 times 1 will give me 2. That means for factorial 2, I got a result for 2. And then I can do 3 times 2, which will be 6. And 6 will just be the result for factorial 3. Right? And then if this is 6, I got 4 times 6. That will give me exactly 24. That means eventually I got 24. Basically, this is how it works in general. You got some original problem which might be big to begin with. And then you have to go deeper and deeper onto the tree until you reach the base case. Once you reach the base case, you have to go back to each level that you visited before and eventually get to the original problem. Okay? That's how it works. But now this is only the tree version. I would say once you get familiar with the idea about recursion, this will be the recommended way to go. That's actually give you the big idea. But for the very first 2 examples for Factorial and Fibonacci, I will show you the stack example as well, just to get more understanding. Okay? So now, keeping this tree in mind, let's try to see how we can use a stack using simply just push and pop to see how we can trace the recursive method. Okay? Again, use the same example. I'm going to trace factorial 4. Okay? And I'm just, again, let me clean the diagram over here, and then let's do from scratch. Now, let's imagine that in the tester code, we're trying to do factorial 4. That means we're calling this method over here, where n is simply just 4. In order to keep track at the runtime, we're going to push onto the stack to say, currently, we are executing factorial 4. Okay, so you'll be pushed onto the stack. The execution will be done when it is popped off from the stack and the stack becomes empty eventually. Okay, we'll see. So now the current value for n is simply 4. We're going to go for the else branch, don't you agree? Right? And then the result will simply just be 4, let me just write from backwards. 4 multiplied by factorial 3. Agree? Factorial 3. 4 minus 1 is 3. Okay? So far so good. And then you can see that because factorial 3 is more like another method call, so we cannot reach to this line just yet, because we got to finish that execution first before we can reach the next line for factorial 4. So what we will do is we're going to somehow execute this first. Okay? So how do we do that? Let's see this. I'm going to use a different color over here. Let's use pink. Okay? That means I'm going to now do the execution for factorial 3, in which case I'm going to make the same block of code for factorial is going to be executed for multiple times. Every time you try to make a recursive call. So now it's going to be factorial 3. So now n would just be 3, in which case we're going to stack on top factorial 3. Right? So now that means factorial 4 is set to be currently suspended until factorial 3 is finished. Okay? So now, how do we do factorial 3? Well, we know that we should still go to the else part because it's not the base case yet. So what we will do is we're going to say it's going to be 3 multiplied by factorial 3 minus 1, which will be 2. Right? So now for factorial 2, we're going to do the execution. Okay? Again, let's use maybe blue. Now, factorial 2 is going to call the same block of code for n. So now the n value will be just be 2. So that means we're going to push this particular execution. So now I'm going to say factorial 2. So what does that mean? That means currently we're going to execute factorial 2, whereas factorial 3, factorial 4, they're all suspended. We'll get there eventually. Okay? Now for factorial 2, we know that we also have to go to the else part, right? And in that case, it's going to be 2 multiplied by factorial 1, right? Now for factorial 1, we're going to do it as well before we can finish factorial 2. Again, let's use it orange maybe. So now, in order to execute factorial 1, we're going to call the same block of code with input 1. And what should we do? Push onto the stack. So we'll say factorial 1 is now going to be executed. So now when we try to execute factorial 1, again, we're going to the else part because it's not a base case just yet. Okay? So now to execute factorial 1, what we will do is we're going to say 1 multiplied by factorial 0. Okay, we're getting somewhere. We're getting there. So now let's see what's going to happen is, finally, let me use maybe deep blue. So now 0 over here is going to be another recursive call. So that means we're going to call the same block of code once more, 0 over here, right? That means put factorial 0 onto the top. Before I move on, you can see that how many suspended execution for the factorial I have got, right? Every time when you try to make a recursive call, that means the current execution is going to be suspended on the stack. You try to put something new onto the top, okay? Once you reach the base case, that means it is time to actually clear the stack, start clearing, okay? So now, let's go on and see how to finish that. So now we're going to execute factorial 0. We know that we're going to go into this particular branch over here, right? So that means we're going to say result is assigned to 1 over here, and then return the result. That means we're going to finish factorial 1 right away, okay? We don't have to have any further recursive call. What's going to happen is like this. Whenever you return, that means this particular execution of the method is going to be pop off from the stack. It's just finished. So that means factorial 0 is going to, I'll say, return 1 in this case, right? And then it's going to return 1, and then it's going to be pop off. I'm just going to remove that. And now, as soon as this is done, what's the current top for the stack? Orange 1, factorial 1. That means now we should go back to factorial and finish that. Okay? Now, factorial 1 is the orange 1 over here. You can see that it's orange 1. Used to be 1 multiplied by factorial 0. But now since we got the result of factorial 0 return being 1, so that means this part over here is simply just 1. Right? So now, to calculate the orange part, it will be 1 multiplied by 1, which will be 1. That means the result for factorial 1 will just be 1. That means factorial 1 is now going to return 1 over here. And then after that, we're going to pop it off from the stack. Okay? After that, we are going to deal with factorial 2, the blue one. Okay? Now, in order to deal with the factorial 2, the blue one, which is over here, we used to be suspended just because we were waiting for the result for factorial 1. But now it has been calculated. Factorial 1 as return from here is simply just 1. Over here, right? So that means to really finish the calculation for the blue, it's going to be 2 times 1, right? So now that means we're going to get 2 times 1 over here. That means this part here is going to return, well, 2 times 1, just be 2, right? And then we'll pop it off from the stack. Okay, that will be 2 over here. So that'll be the result to be returned. So now what should we deal with? The pink one, factorial 3. If you go to factorial 3, which is over here, used to be suspended, and we are waiting for the result for factorial 2. But that one has been returned already. So that means what we will get is, for this particular one, factorial 2 is just going to be returning 2. So we got 2 over here. So now what should be the result for factorial 3? 3 times 2. Right? 6, good. Let me just highlight it. So now for this part here, it'll simply give me 6. So that will be return 6. And as soon as it's returned, pop it off. Okay? So now for returning 6, so now what we get is, we have to go to finally, the last one on the top, factorial 4. So if we go back to factorial 4, over here, used to be suspended because we were waiting for factorial 3 result. But now that one has been returned, which is 6 over here. And then for 6 over here, so that means for the green one, it's going to be 4 times 6, which will be 24. Okay? And now that means this part over here is going to be 24. So eventually you're going to return 24 for the result. And then pop it off, and we are done. Okay? Any questions about this? As you can see, let me just say one thing before you ask a question. As you can see, there are 2 ways to trace the same recursive call from factorial 4. The first version I show you to you on the top, that will be, once you get familiar with the recursion, that's how you should do it. As you can see, if you simply do the stack version, it's a little bit too low level detail for the runtime execution. You can still do it, but I would say once the example gets complicated, it's just a little bit too difficult. But you have to know. Okay? Questions?
So every time we make a call to the
Yeah. Correct. Every time you make a call, push onto the stack, and every time you get a return from the previous call, you combine the result and then go on with the current one. Yeah.
And if the program gets too big, let's say you want to do factorial of like 100, would the big O of this be like 2 to the n? Like
Yeah, you're basically talking about the performance for recursion. Let's not worry about it just for now. Yeah. Okay, guys, let me just try to strengthen your understanding a little bit. Okay. So now let me just give you an alternative version of the factorial. And if you can tell me what's going to happen, okay? I'll give you two alternatives. Let's say this. Either I can say, let me just call it fact, integer, let's say version number 1. Factorial integer I. And over here, I'll simply say, if I is equal to 0, oh, actually, you know what? I meant to say the other way. First of all, let me simply say just factorial integer result. Let's say I don't have any condition. I simply say result is assigned to factorial over here. Oh, you know what? I should say n, not I. N, okay? N multiplied by factorial n minus 1. Return the result. Okay? Let's say the only thing I changed was by removing the if part. So now I've only got the else part, so there's no condition. Now, if I try to do factorial 4, what's going to happen? I heard 0. Stack overflow, that sounds more promising. Let's see how it's going to happen conceptually, and then I encourage you not to try on your computer. Okay? Don't try it. Okay? If you try it, you'll find that your computer is getting louder and louder on the fan. Louder and louder. Eventually, it might just slow everything down. You have to brute force that to restart. Yeah.
Can we somehow improve that and stop that from happening?
Basically, what's going to happen is on Eclipse, if you simply try this, it's going to tell you stack overflow. Yes, I think. But if you try that on another programming language, for example, C, if you try to execute that from the command line, it's definitely going to eat up all the resources. Don't try this in person lab. It might get deactivated for your account if you try that. Okay? Yeah. Anyway, I was joking. Of course not. Yeah. Okay, let's see why this can happen. Okay, let's be logical here. There's a very common error for recursion. The problem over here, number 1, you get a lack of base case. Base case is really once you reach the base case, it can stop popping off the stack, right? That's basically what a base case is. If you have no base case, that simply means it's going to happen like this. You start with factorial 4. To do that, you got to do factorial 3. To do that, you do factorial 2, and then factorial 1, and then factorial 0. In the previous case, we do have a base case to stop growing the stack. But now, nothing will stop you from growing the stack. You go to factorial minus 1, factorial minus 2, and so on. That's the problem. Okay? That's a very common mistake. Okay? Are we okay with this? The reason I'm showing you this is to make sure every time once you finish your recursion, make sure you got base case. Okay? Now, another one. Another very common error. Version number 2. Still factorial. Integer, factorial, integer, n. Let's say I do have a base case. Let's say I do. Integer, result, and then I say if n is equal to 0, I would say result is simply assigned to 1 as before in the previous slides. Otherwise, okay, this is what I would do. I would say factorial, oh, let me just say n first. N multiplied by factorial n. Now I do have the base case. It's going to work. What's the problem here? Yeah, the problem is, remember one of the principles I said, when you try to solve a problem recursively, you want to make sure you split them into strictly smaller problems, right? So over here, the problem that you're trying to solve over here, factorial n is not strictly smaller than the original problem n. That's the problem, okay? So now what's going to happen? Again, let's do factorial 4. Now, I try factorial 4, then it's going to be n times factorial 4. Put it under the sec, and then to do that, factorial 4 again. And you will do factorial 4. Keep going until it kills your computer, all right? So now what's the problem here? The insight is you're lacking of a way to reach the base case. You keep solving the original problem. You're not really making any progress. You're not really letting the fairy gun model to help you on the smaller problem, if I want to use that analogy, okay? Okay, so now for these two versions over here, so these are the counterexamples you want to avoid. Whenever you want to design your recursive algorithm or methods, so you want to make sure, first of all, you want to get base case. And second, you want to make sure every time you want to make a recursive call, make sure the input value is strictly reduced on its size. So you can eventually get to the base case. Are we okay with this? Okay, good. Yeah, I think that's really important to understand how you can get things to work. Let's say in the final exam, because most likely the exam will be on the paper, right? So if you're asked to write a recursive method, you want to make sure, since you have no computer besides you to check, right? You want to check at least these two. You got base case, and then you also got strictly smaller problem for every recursive call, okay? Now, that's about factorial, and let's solve another one in detail, and then we'll get to a little bit faster, okay? The next one, of course, over here, just a little bit bigger problem. You can go over the slides, but we have talked about them already, okay? So this one just, you can, about suspension and activation of the stack, okay? What I would do is, let's trace another problem, Fibonacci, okay? Do you know what a Fibonacci sequence is? If for those of you who do not know, that's okay. I will review that very quickly with you. A Fibonacci sequence looks like this, okay? You start with 1 and 1. We simply use a Fibonacci sequence. Any number at a Fibonacci sequence, we say f, maybe n. And n can be starting from 1 until infinity, okay? So we say that f1 is simply just 1, always. f2 is always 1. Starting from the third number, you always try to say, for example, f3 is going to be f1 plus f2, okay? 2. What about f4? It's going to be f3 plus f2. It'll be 3. What about f5? You got f4 plus f3. You got 5. And then you got 8. You got 13. You got 21. You got 34, and etc. Okay, that's Fibonacci sequence. Anybody not comfortable with this idea here? Okay, good. Now, what we want to do is, we want to say this is the problem we are trying to solve, Fn, over here. And n can be starting from 1 until anything that towards infinity, mathematically speaking. Now, how can we solve this recursively? Okay, how do we do that? So now, let's try to apply this, our principle, okay? If you want to design a recursive solution to a problem, always think about base cases. What can you solve first without further processing? Well, apparently you can see that for a Fibonacci sequence, we say that always f1, f2 is always the same, right? So that's why we can say that if I want to calculate fn, it can be divided into at least 3 possibilities. It can be just 1, base case number 1, if n is equal to 1, right? Or it will still be 1 over here if n is equal to 2. Now, what about the recursive case? Recursive case means I'm going to assume I do have the solution for some strictly smaller problem. What can be a strictly smaller problem? For example, fn minus 1 is a strictly smaller problem than just n, right? And also, fn minus 2 is also strictly smaller problem. Also, if you like, fn n divided by 2 is also a strictly smaller problem, right? So there's no way stopping you from coming up with the expression for the smaller problem. But now for our particular purpose, how many subproblems do we need in order to calculate Fn? 2, right? Given if you want to calculate Fn, so what problems do I need to solve first? F of n minus 1 and f of n minus 2, right? So that means what I need to do is I can say if n is larger than or equal to 2, that will be the recursive case. I assume I have the solution for n minus 1. n minus 1 is strictly smaller than the original one, so I won't have stack overflow. Also, I assume I also got the problem for n minus 2, right? Again, that is strictly smaller than the previous one, so I don't have any stack overflow. And now, so these are basically 2 distinct values for the same problem with a strictly smaller input size. I want to combine them somehow. How do I combine them in this case? Should I say multiply just like before? You can see the way we combine the recursive result was by using multiply in the case of a factorial. Should we use multiply here? No, good. We should use plus. Okay, over here. Okay, you can see, again, let me recap. We are trying to solve this particular problem over here of size n. And we got basically 2 categories of cases. Category number 1, base cases, which we can turn the solution right away. If the problem is too big for us to solve, if it's larger than or equal to 2, we'll split that into 2 subproblems. It doesn't have to be 2, but typically it may be 1 or 2 or 3, typically. And then this is a strictly smaller problem, and this is a strictly smaller problem as well. And then we combine these 2 solutions together using some operator. Okay? Again, you will see this kind of solution pattern occurring over and over for all the examples. Are we okay with the expression here? Okay, so now, question for you. How do you turn this into a Java method? It should be rather straightforward, right? You define a method that will return an integer. And then we'll also take an integer as input. You try to make 2 recursive calls in the program method body. Okay, let's see how we can do that. If you look at that, this is exactly what we just came up with together. So now, how do we translate that? And then we'll trace it again using stack and tree. Okay, so let's just commit fib for Fibonacci. It's going to take an integer n, return an integer. And we got the result over here. We got 2 base cases. If it's equal to 1 or equal to 2, we simply return 1 and 1 right away. If it is neither the case of the base cases, I would say make a recursive call to the same method over here with a strictly smaller problem, n minus 1. Also make another recursive call with another strictly smaller problem, n minus 2. Right? And then combine the result together with plus. Okay? And then eventually return the result. Are we okay with this? So now the only complication we have is rather than making just a single recursive call, as in the factorial case, we're making 2. So that's why I want to show you once more how we can trace this particular method here using stack and tree. Okay, that'll be the last example we will use a stack. Okay. The principle is very easy. That's also why I want to show you how you can trace using a stack. When you actually got one recursive call followed by the other. So what does that mean? That means before I can terminate the execution for the earlier execution for the recursive call, this part here simply wouldn't be pushed onto the stack. That's what you will see. That means it's not going to happen just yet. Okay, that's something we'll see. Okay, again, I would like to first of all give you some high-level detail about how you can trace the program using just a tree, and then I will use the stack. That's the progress. Okay, let's see the tree. That's the easier version. Let's say I want to do Fibonacci of 4. Okay, easy one. Okay, that will be sufficient enough. You will find that to trace this one is already quite complicated using a stack, but that will give you just the idea. Okay, let's use a tree first. I'm going to use something similar to the tree over here, something similar. Okay, let's see how we can do it. Let's see this. We start with Fibonacci of 4. We know that 4 is none of the 2 base cases, right? So now we know that in order to calculate this, we have to do the following. We had to say Fibonacci of 3 plus Fibonacci of 2. right? Now, in order to calculate Fibonacci 3, we have to do, it's not a base case yet. We're going to do, let's say this. We're going to do Fibonacci of 2 plus Fibonacci of 1. That's what we're going to do, right? Now, we know that Fibonacci of 2 is already one of the base cases, right? It's going to be 1. Fibonacci of 1 is also going to be one of the base cases. That'll be 1. So that means 1 plus 1 will give us 2 for the Fibonacci of 3. And now, since we complete this left recursive call, we can now move on to this particular one, right? And this one is already a base case. So that means that one is going to be returning 1. So that means eventually we can get 2 plus 1, combine them, we get the result for Fibonacci 4, which is 3. That's the overall picture. Okay? Questions?
Why wouldn't you just say if n less than or equal to?
So you can see that, let me see if I get the question correctly. So you can see that over here, so there are two possible base cases, right? It can be either when n is equal to 2 or when n is equal to 1. So you can see the base cases we got is over here. So we got Fibonacci 2, Fibonacci 1. That's why we don't go any further with the recursion tree. And then also Fibonacci of 2.
Can you just say n is less than 3?
Can you get n less than or equal to 3?
Can you just say that?
So n is less than 3?
Will that work?
Okay, how about, yeah, I see what you mean. Let's say this. Let's try a different one. If I simply want you to calculate Fibonacci of 3, let's say, okay? So what we'll do is, let's say we start with Fibonacci of 3, and that one will tell us, well, Fibonacci of 3 is not a base case yet, right? 3 is neither 1 nor 2, right? So that means you should do Fibonacci of 2 plus Fibonacci of 1. So now both of them are the base cases. That means this will be just 1. This will be also 1. So that means eventually it will be 1 plus 1, that's 2. Right? Yeah, good. Guys, are we okay with the first view? Okay, you get a big picture. So let's now get down to the stack for the final time. Okay, I think it's worth doing. Okay. Let's now see how we can trace it. Let's be very careful. So now let me tell you the principle again. Every time when you want to make a recursive call, you push that particular new call onto the stack. Okay, and then when we got 2 consecutive recursive call, we make sure we finish the left one before we ever put the right one onto the stack. Okay, these are the principles. Let's see how we can do it quickly. Okay, let's be careful here. All right. Now let's say we try with Fibonacci of 4. So that means n will be just 4. Okay, that means we push Fibonacci of 4 over here onto the stack. In this case, we skip the first 2 cases, we go to the else part. And now, result is going to be Fibonacci of 3, 4 minus 1, plus, oh, actually not yet. Okay, let's be careful. So now we don't even get to the right part because now we should really finish Fibonacci of 3 first. Okay? In order to calculate Fibonacci of 3, right? So we're going to make a recursive call. So what I would do is, I would use another color, let's say pink. So now in order to calculate Fibonacci of 3, that means I'm going to call the same block of code with the n being 3 over here. So that means I'm going to push Fibonacci of 3 over here onto the top of the stack. All right? Now, what's going to happen? What's going to happen is we are also going to skip the first 2 cases over here. And then when we reach the else part, it's going to boil down into Fibonacci of 3 minus 1, which will be 2. And we don't get to the right part until we finish Fibonacci of 2. Okay? That means now we're going to handle the Fibonacci of, let me use blue. We're going to do Fibonacci of 2 over here, right? Now, Fibonacci of 2 is going to be 2 here. So I put Fibonacci of 2 onto the stack. Now we are lucky. We get to the base case, right? So now for 2 over here, that means we're going to reach n equals 2 over here. That means result will just be 1, and then we simply return just 1. That means for Fibonacci 2, we simply return 1. And then pop it off from the stack. Okay? Now, good. So now, what should we go on? How should we go on? Where do we go to? Fibonacci of 3, right? Because you can see Fibonacci of 3 is now the top of the stack. So now we go back to the pink part over here. So that means we know Fibonacci of 2 over here is simply just 1. Okay? And then we continue with the plus. And then we say plus Fibonacci of pink one is basically just 3 over here, right? Remember, okay? I mean, you can switch back to pink. So now we still talk about the pink. So that'd be 3 minus 2, 1. Fibonacci of 1. Let me just be a little bit careful with the color, otherwise you cannot see. Now Fibonacci of 1. Okay, now in order to do Fibonacci of 1, again, I'm gonna do this, and then, so that means we're gonna execute the same block of code with 1. Okay, and then we're gonna push Fibonacci of 1 onto the stack. And now to execute this, again, we are lucky. That's the base case. Fibonacci of 1 is going to reach the first base case over here, and then result will be 1, and then we're gonna return 1 again. Okay, that means Fibonacci of 1 is gonna return just 1 over here, and then you're gonna pop it off the stack. Now, where should we go to? Fibonacci of? Are you sure? Well, after popping off Fibonacci of 1, what's the top of the stack? Only look at the diagram. What's the top? 3, exactly. Follow the diagram. That's why using the stack has this advantage. So that'll be precise. You got to follow faithfully from the diagram. So that means we go back to Fibonacci of 3. That means now since we were waiting for the result for Fibonacci of 1, and that one has just returned 1. Oh, sorry, wrong one. That one has just returned 1. So that means this guy here will be also 1. So now 1 plus 1 will give me 2. So that means for this particular call, for the Fibonacci of 3, I'll simply just get 2. All right? And then that means Fibonacci of 3 is going to return just 2 over here. And now once I got the 2 over here, where should I go? And then, of course, pop it off. Now, where should we go? Fibonacci of 4. Good. Thank you. When we go to Fibonacci of 4, which is the green one, you can see the green one is over here, right? That's where we got suspended, right? Because we were waiting for Fibonacci of 3. So now Fibonacci of 3 just returned back to us the value of 2. Okay, that means we can continue with that. Let me use green to continue. And then you would say plus, and now the green one is about n being 4. So that would be n minus 2 would be Fibonacci of 2. Plus Fibonacci of 2 over here. So now, in order to execute Fibonacci 2 over here, again, we have to execute this block of code with 2 again. And push that onto the stack. Fibonacci of 2. Are we lucky? We are. We are not in base case. So now Fibonacci of 2 is going to reach this base case again. And we're going to return 1 and return 1 again. That means for this part here, we're going to return 1 and then pop it off. Where should we go back? Fibonacci of 4, right? The green one still. That means what we will do is we used to be suspended over here waiting for Fibonacci of 2. And now that one has returned 1. So we put 1 over here. Now for the green one, finally, what you will do is, since previously we got 2 from Fibonacci of 3, and also we got 1 from the Fibonacci of 1. So 2 plus 1 together give us 3. That means we're going to return 3. Right? So that means Fibonacci of 3 is going to return 3. Okay? Pop it off. We get a final result, 3. Are we okay? Yeah. I'm doing better. I was trying Fibonacci of 5 last year. This year I gave up, just Fibonacci of 4. Okay, no mistake so far. Good. Are we okay with this idea? If you really want to practice how to trace using a stack, try Fibonacci of 5. Give it a try. Okay? Not really, but as long as it eventually terminates, you're fine, right? Okay. Yeah.
It's pretty bad.
It's pretty bad. The performance is bad, but let's not worry about performance just yet. Let's just understand conceptually. Again, as far as recursive design is concerned, you want to make sure you avoid the two mistakes I said. Either you don't have a base case or you don't have reduced the problem size strictly. Okay, so these are the two mistakes you really want to avoid. Okay. So guys, do we have any question about Fibonacci here? Go ahead. Sure.
The one, yes, this one.
Yeah.
So would a strategy be when you're dealing with the Fibonacci drawn out the
You mean the tree over here?
yes, the tree.
Yeah.
So instead with Fibonacci of 2, would the strategy be that if it doesn't have like any leaves attached to it, try to go down that to solve first and then go back and do the one?
Yeah, basically you can see that in the tree. As soon as you reach, for example, a Fibonacci of 2 over here, what you will do is you will check the code to see which branch you will go into. In this case, it will just go into n is equal to 2, and then it will just do something to the result and then return eventually. That means you don't have to go any further from the tree. Yeah, that's a base case.
Just keep it simple, go like down the branch that has like less items on it.
No,
Like,
no.
just so you go back to like
Well, thinking this way, if you look at a tree, let me just make it clear to you. Let's try to look at the Fibonacci number tree again. Let's say this. Fibonacci of 4, which we know should be Fibonacci of 3 plus Fibonacci of 2. And for this one here, we know it's going to be Fibonacci of 2 plus Fibonacci of 1. Okay, like that. Okay. Now, there are two kinds of nodes on the tree. There are two kinds. Again, you're going to learn about tree a lot in 2011. Let's not go too deep into it. Okay, that's not that's not what you're supposed to learn for this course. So I'll highlight this one here, and this one here, versus these two. The green versus the orange. If you look at the orange ones, those are so-called leaves of the tree, which means below them, you don't have any further tree. That means there's no further recursive call. That means you get a result right away, right? The orange one, Fibonacci of 1 or Fibonacci of 2, you simply get a result right away. But the green ones, like a Fibonacci 4 or Fibonacci of 3, those are the ones you cannot simply know the result right away. It must depend on the result of a subtree, right? Good. And just a little bit preview of your 2011, even though I'm not teaching you that. In 2011, you're going to learn about lots of algorithm giving a tree. How can you figure out the maximum number of a tree? Basically, well, I shouldn't really go too deep into it, right? Okay, anyway, you'll learn about it, 2011. Once I go into it, I wouldn't stop. Okay, now let's go to the next problem, okay? Okay, so now, from now on, of course, that's a Fibonacci of 5. I do encourage you to try stack on Fibonacci of 5 at your own time, okay? Try to restrict that within 1 hour, hopefully, right? It shouldn't take that long. Okay, now, we're going to talk about several recursive methods on a string. But let me just make sure we are on the same page. Let me go over one block of code very quickly with you to make sure you're okay with the string. I'll also make the source code available to you. Okay, so now let's just do that very quickly. Basically, I want you to get very familiar with two methods, several methods for the string. One is called substring. Another one is called, over here, char_at. For those of you who don't know about the method, that's okay. I'm going to illustrate to you very quickly. The char_at is very easy. You can think about, if I got a string, let's say A, B, C, D, you can think about it as an array of characters with 4 characters. You got A, you got B, you got C, you got D. And arrays start with just 0, 1, 2, 3. Okay? So when I say character at, if I say character at 2, what would that be? C. Good, you got it. As easy as that. Good. Another one I want you to learn about is, let's say this. Let me just highlight another one here. Let's say substring. Substring is a little bit tricky. I want to get part of the string, okay? If I say 0, 4, intuitively you might think this doesn't make sense because there's no index 4 for this particular string, right? However, when I say 0, 4, I'm really talking about this particular interval. right? For those of you who learned about calculus, well, nothing to do with calculus. I'm just saying you might have seen this notation in calculus course. The index 0 here is a closed interval, and the 4 over here is basically open interval. So when I say 0 and 4, I'm really talking about give me the string from position 0 until and including position 4 minus 1. So what this will give to me will be this part, the whole string. Are we okay with this? Okay, so two methods we want to get used to, substring and char@. Are we okay? Okay, let's get to solve some interesting problems, okay? Now, first one, palindrome. Okay, for those, do you know what a palindrome is? If you don't know, let's explain, okay, before we can solve it all together. A palindrome is simply a word that can read the same forwards and backwards. Can you give me any example for palindrome? Huh?
Or race car.
Race car, yeah, that's a typical one, yeah, race car. Or madam. Madam, right?
Was it a car or a cat?
Car? It's called a,
Palindromic sentence.
sorry, say it again.
It's a palindromic sentence. Was it a car or a cat?
Oh, it's a word. I'm talking about word. Only a single word. Yeah. Okay. Yeah. We got different palindrome here. For example, okay. Let's say is empty string a palindrome? Wow. Right. Read the same backwards and forwards. Right. And if I've got true. Okay. A. Okay. And then if I got madam, it is. And race car. Yes, that's good. Man. No. Very good. Okay. Good. You know what a palindrome is, right? Now, from 1022, you would know how to write a loop to check if a string is a palindrome. I'm sure you know how to do it. Let's now forget about loop. How do we solve this recursively? Okay, I will lead you to the solution, okay? For those of you who know the solution already, please keep quiet, okay? So everybody can follow my hints. I'll give you a little bit hints over here. Let's try to get some intuition over here for, again, the problem itself is very easy. I want you to really understand how we can apply the pattern for solving problems recursively to the recursion, right? Let's just see this. We know that race car is a palindrome, okay? Now, let's have another one. We know that, oh, how about this? Race cars. Is that a palindrome? No, very good, okay? We know that this is a palindrome, whereas this is not, okay? Let me give you some visual hints to see if you're smart enough to pick it up, okay? I'm gonna do the following, I'm just gonna use color. Can you see what I'm doing here?
Remove the first element.
Oh, no, just wait. Just observe what I'm doing here. So now, if you look at these two strings, I know the first one should be true, is a palindrome. The second one is not, so that should be false. Let's look at the second one. What am I doing here? Basically, I'm trying to split the problem into some strictly smaller problem, right? So now, okay, guys, just, all right. Okay. Let's look at the second case over here. Basically, I'm trying to show you how you can split the problem into another strictly smaller one. I'm basically saying that for the first one and the second one, this is how I'm going to split. The way I'm going to split is to take out the first character and the last character. So once I take out the first character and second character, like this, so this will be the strictly smaller problem. Okay, this is a smaller problem. In order to be a palindrome, what's the requirements? Okay, anybody just before I say that, just based on what I just colored, the string, what will be the requirements to be a palindrome? Yes, go ahead. Yeah, when you say, just be careful. When you say every character, that sounds like you're running a loop, right? Yeah, okay. So anybody want to try before I say it out? Yes. What do you mean every substring?
From beginning to like beginning to the end.
Well, but when you say from beginning to the end, you're talking about the original string, right? You're not really making the problem smaller, right? So you're getting there. Anybody want to try? Yes. Yeah, go ahead. Yeah. Substring. How do you get that substring?
Every iteration, break it down
How do you break it down?
using the substring method.
How do you use a substring to break it down? Yeah. Sorry, I'm sorry for pushing you. Okay. Basically, this is how you do it. Okay. Basically, I'm gonna create substring for sure. This is the idea. In order to be a palindrome, this is the requirements. The first character and the last character must be the same. If they are not the same, you don't even bother to compare them, right? And if the first character and the last character are the same, and then there's a chance to be a palindrome, okay? If there's a chance, I take out these two and get a substring, so this will give me a new problem to check if there's a palindrome or not. Okay, so now, thinking this way. If I have a string S, let's see over here, right? So now if I want to check to see if there's a palindrome or not, I want to see if the first character, I will show you exactly how to do it programmatically. If the first character of S is equal to the last character of S. And then I can use this operator over here, right? Which means if this is already false, I don't bother to evaluate the right-hand side. And then I'm going to make a recursive call to say is palindrome and then substring. And substring over here is going to be the original string with the first character and second character taken out. Okay? Guys, do you get a big idea? So this is what I would suggest whenever you see something to be solved recursively. That's exactly what you want to do. You don't want to get to the code right away. That's not the way to go. You want to sketch idea just like this. Using some examples, think about what the base cases are, and then go from there. Okay, now one more question for you. Since we're going to define things recursively, what would be the base cases for this? What would be the problem that's so small that we don't even bother to go to recursive call? Empty string, that's good. If empty string, that means should be a palindrome, right? Yeah, if length is equal to 1, then that should be palindrome right away, right? If anything that goes beyond length 1, then we can solve recursively. Okay? Now let's see how we can do it. And then I'll trace 1 together with you. I'll trace 2. Okay? Okay, let's look at the code over here. This is just conceptually how you can do it, exactly what I said. Okay? Now, let's look at the code. isPalindrome is going to be Boolean method, which is going to take a string, and then if the length is either 0 or 1, just return true, right? Otherwise, take the first character, take the last character, and then try to see, and also take the middle part. Middle is simply the substring between position 1 and also word.length minus 1. I'll let you work out why we need word.length minus 1, okay? Just by applying what substring really means. Okay, I'll leave that part to you. That's when it's technical, okay? And then we say that first character is the same as last character and is palindrome, the middle. And middle is guaranteed to be a strictly smaller problem compared with the original word, right? Agree? Good. Now, let's trace. I'll give you 2 examples. And let's make it even easier. Let's consider 2 cases, okay? Let's say I have, let's say, A, B, B, A. Okay? Basically, I start with, is A, B, B, A a palindrome, right? Basically, it will split into the combination of whether the first character is the same as the last character. A equals A, and is palindrome what? BB, right? Just this one here. Okay, BB. And then, now, remember short circuit, right? This part is simply true. So we do have to evaluate the right-hand side as well. So we have to go on. And then it's palindrome over here, BB. So what do we do? Again, split it. The first character will be B, last character will be B. Now it's going to be interesting. B equals B, and is palindrome what? Empty string, right? If you look at the way we do the substring calculation, you will see that it will work. Okay? It's going to be just palindrome, empty string over here. So now we know that B equals B is true. That means we do have to go here, and this, we're lucky, base case, which would just be true. So true and true give us true. Okay with this? Let's do one more. Okay, let's say we do another one. What about, let's do something that's not a palindrome, okay? Let's say we got A, B, C, C, A. Okay, this one will be interesting to see, all right? So now, is this a palindrome A, B, C, C, A? So we're gonna split it into into first and last character. That will be boiled down into A equals A, and is palindrome, and now the remaining part will be B, C, C, right? This part here, we know it is true. That means we do have to go to the right-hand side. In that case, we have to now do the following. Get these two, right? First and last. So that would be B equals C, and we get left, C. And is palindrome, and then you have C over here, right? Now what do we do? Well, do we have to bother evaluating this? No, because this part here is already false. Short circuit makes sure you don't even have to go there. So this part is already false. And then false and true overall is going to give you false. Guys, are we okay? Okay. How about just 2 more minutes? Okay, 1 or 2 more minutes. A problem here for you. How do you take a reverse of a string? Again, you know how to, from 1022, you know how to do a reverse of a string, right? If you got ABC, you want to get CBA, right? This is what I would do. I want to show you the code, okay? Now, I will give you a visual hints, okay, as before. This is what I would do. Reverse. I'll make a very long string. That's a string. That's the input. We know the output should be I, H, G, F, E, D, C, B, A. That's a reverse, right? Now I'll give you visual hints. Okay. Think about it for 30 seconds, and then I'll mention it verbally, and then we are done. Think about it, okay? So what do I mean by this, really? Apparently, the orange part is not really equal to each other, is it? It's not really. But the two orange parts are somehow related to each other, right? The red part is the same, but it's in a different position of the two strings, right? Anybody want to try? Just describe informally. What I like about solving recursive problem is, once you get used to it, you find that it's more natural to think about than loops. But in the beginning, it's the opposite, usually in the beginning. Yeah, give it a try, yes.
First you try to add the first digit to the end.
Yeah, so you want to take the first character from the input and add it to the end of the output, yes. And?
Remove it from the index.
Yeah, and then remove the first character from the input, and then?
Recursive, you call it again.
Yeah, sounds good to me. Basically, this is what you got to do conceptually, okay? What we do is, let me just mention this and one more thing, and then we are done, okay? Now, because there are two ways to solve that recursively, I'll show you both, okay? Basically, this is what you do. You take the first character of the input, and then recursively call reverse on the remaining part of the string. Whatever result you get from the fairy godmother, from the recursive part, you put it as the front of the output string and put this at the end. Are we okay with this? One more thing and we're done. There is another way to solve this. Let me show you very quickly and you'll get it right away. Let's talk about the same string. A, B, C, D, E, F, G, H, I. And then I got I, H, G, F, E, D, C, B, A, right? Now let me hide that a little bit differently. Well, apparently this highlight is different from this highlight, right? But they represent different solution recursively to that one. Can anybody try to describe this informally, and then we're done? Anybody want to try? So what are we doing here, over here? Apparently the orange part is still like the recursive part, right? And the orange part, again, are not exactly equal to each other. They pretty much represent the recursive call to the sub-problem there. And then the pink part is represent a way to insert this character into somewhere in the output stream. So now, anybody want to try? Whoever is very keen to go, you should try. Otherwise, everybody's stuck here, right? Yeah, go ahead. Yeah. Yeah, exactly. Okay, let me summarize and we're done. Basically, what you do is take the last string over here and then recursively call the remaining part of the string, put the last character as the first character of the output, and then apply the recursive result as the remaining part of the output string. Okay, now we'll look at the code next Monday. Okay, see you next week.